Welcome back to the deep dive. Our mission here, as always, is pretty simple. We take complex, really cutting-edge research and we distill it. We find the crucial insights and turn them into the knowledge you need to be, well, immediately well-informed.
And today, we are tackling a fascinating problem.
We really are. It's something that exists in, nearly every high-stakes field you can imagine, from engineering design all the way to medical diagnostics.
It's this unavoidable reality of conflicting goals.
Exactly. The machine learning world calls it multi-objective optimization, or MOO for short. Think about it. You want your financial trading algorithm to be incredibly accurate, but you also need it to execute trades in, milliseconds?
Right, or an autonomous vehicle. You want that system to prioritize safety above all else, of course.
Of course.
But it also has to be computationally efficient enough to run on a tiny little onboard chip.
So you have accuracy versus speed, safety versus efficiency. These goals are, they're fundamentally at odds.
And when those conflicts come up, that's when you turn to optimization techniques to find the best possible compromise.
And we're focusing today on one of the most reliable and maybe most interpretable methods for solving MO. It's called the lexicographic method. But, and this is the core issue for our deep dive, we're looking at some really revolutionary research that targets its single, glaring, long-standing Achilles heel.
The arbitrary selection of the tolerance parameter. It's basically been done manually.
Essentially, yeah, ad hoc.
And that manual selection, it's introduced a critical vulnerability into what are otherwise high-performing models. Just think of the stakes.
Right.
When these tolerance values, and they dictate how much compromise the main goal allows to the secondary goal, when they're chosen based on a human guess or just some vague intuition, it injects this profound uncertainty and inconsistency.
You end up with a suboptimal solution.
Very often, yes. Highly suboptimal. They might sacrifice far too much accuracy just for a tiny bump in speed, or the other way around, all because that initial guess was just wrong.
And I imagine that drives up computational costs, too.
Unnecessary costs, exactly. And you end up with models that you just can't consistently reproduce. If you can't trust the input parameter, well, the output model is inherently compromised.
What's really remarkable here, and this is what makes this deep dive so timely, is that for a long time this issue was, kind of ignored in the literature.
It really was.
For all the brilliance that's been applied to optimization algorithms, there's been this glaring lack of systematic research on how to explore or even automatically resolve this tolerance issue in the lexicographic method. It was like a known problem that nobody had built a tool to fix.
That's absolutely right. And this study, it steps directly into that critical gap. It's really charting unexplored territory by applying machine learning principles to solve a foundational optimization problem.
So our mission today is to unpack precisely how this novel automated algorithm provides a systematic, consistent, and robust way to automatically fine-tune this crucial parameter. It's ML helping MOO, optimizing the optimization process itself.
And the results, as we'll see, show dramatic enhancements in model performance across wildly diverse data sets.
Okay, so let's start by grounding ourselves in the multi-objective challenge. We've touched on it, but let's really nail down the scope here. MOO isn't some minor technical hurdle.
No, it's the defining characteristic of real-world decision-making.
Exactly. You are simultaneously trying to maximize multiple conflicting criteria. So let's take a complex engineering problem, maybe optimizing the design of a wind turbine blade.
Okay.
You want to maximize its structural strength. That's objective 1, safety. You also want to maximize energy capture, objective 2, performance. And at the same time, you're trying to minimize the material costs. That's objective 3, economy.
And if you improve any one of those, you're usually going to take a hit on the others.
That's the conflict. And that's what MO exists to resolve.
And this is exactly why the integration of machine learning with these more traditional optimization algorithms has become such a hot area of research.
It makes sense.
Yeah, traditional, rigid, mathematically defined methods, they can really struggle when the objective landscape is vast or, filled with highly nonlinear trade-offs.
Which is pretty typical in modern deep learning problems.
Very typical.
Oh,
so
yeah.
ML introduces adaptability, efficiency, and a way to sort of learn the landscape itself, instead of just trying to define it with fixed equations.
So within this world of optimization, the lexicographic method has always had this kind of special status. It's fundamentally based on prioritization. It demands that we establish a hierarchy before we even begin. How does that work at its core?
The lexicographic method functions. I guess you could think of it like a government or a constitution. It establishes a fixed order of precedence for your objectives.
Okay.
So you, the user, you have to declare objective 1 is the most important, objective 2 is second, and so on. And then the algorithm tackles the problem iteratively. It operates like a relay race, where only one objective is the focus at a time.
So it solves for number 1 first?
It optimizes objective 1 until it can no longer be meaningfully improved. And once that's locked in, and only then, does it move on to objective 2. And to make sure that any gains made for objective 2 don't significantly degrade the performance you already got for objective 1.
That analogy of a constitution is perfect. It's like it enshrines certain rights or objectives as non-negotiable before it allows any negotiation on the lesser ones.
Precisely. And this hierarchical prioritization, it offers several really critical advantages. That's why it's so desirable in certain fields. First and foremost, it gives you certainty. It ensures that your critical objectives are never compromised for lesser gains. If you're building a safety-critical system, let's say an airplane autopilot,
Right.
objective 1 has to be stability and safety. The lexicographic method guarantees those primary goals are met first, no matter what it costs. Secondary goals like fuel efficiency or passenger comfort. Failure on objective 1 is just. It's not an option.
Okay, that's a big one. What else?
Secondly, its major appeal is its simplicity and interpretability. If you compare it to stochastic methods, like complex evolutionary algorithms, which, essentially throw a bunch of random solutions at the wall and see what sticks.
A kind of brute force approach.
In a way, yeah. The lexicographic process is highly transparent. You can trace exactly why a particular trade-off was made. And that clarity is absolutely vital in heavily regulated sectors like finance and healthcare.
Because the stakeholders, the regulators, they need to understand the compromises.
They need to fully understand them, yeah.
That makes a huge difference for adoption. I mean, transparency builds trust.
And thirdly, there's the factor of feasibility assurance. By proceeding down this hierarchy, the method ensures the final solution is already guaranteed to be feasible, to satisfy the constraints for all the most critical objectives.
So like in logistics.
Perfect example. In large-scale logistics, guaranteeing timely delivery might be your objective 1. Only once those delivery windows are locked in does the system move on to objective 2, which might be cost reduction. The precedence guarantees that primary constraint is honored.
And this is the moment, right? This is where the need for our topic, the tolerance parameter, becomes unavoidable. Because if you pursue objective 1 strictly, mathematically, until it cannot be improved by even 1/1,000,000%.
You might just cripple your ability to optimize objective 2.
Right. The tolerance parameter is, in essence, it's the governor or the dimmer switch on that strict adherence. It introduces the necessary flexibility. It lets the algorithm say, okay, I've optimized objective 1 to a point where further gains are trivial, but if I accept a degradation of, say, 1% in objective 1, that's my tolerance, I can get a 20% improvement in objective 2.
And that balancing act is what transforms these mathematically perfect but very rigid solutions into robust, practical, real-world solutions.
To really appreciate the elegance of fixing this tolerance flaw, I think we need to understand the pain points of the other big MO approaches someone might use instead.
Absolutely. Because these alternatives often fail precisely because they just can't handle the nuances of the trade-offs or the scale. Let's start with the weighted sum approach. It's the easiest to explain and implement.
How's that work?
You just assign a specific weight, say 70% importance to accuracy, 30% to speed, and then you combine all the objectives into a single composite function to minimize or maximize.
That sounds simple enough, but what's the catch?
Well, the catch is twofold. First, choosing those weights is notoriously hard. I mean, how do you quantify the numerical equivalence between safety and cost?
Good point.
And secondly, and this is more technically damaging, the weighted sum approach often struggles with what we call non-convex Pareto fronts. That's the frontier of optimal solutions. By linearly combining objectives, you often fail to find solutions in the dips or the complex curves of the trade-off landscape.
So you're basically reducing a multi-objective problem back down to a single objective one.
You are. Which means the resulting solution might be far from truly optimal in the multi-objective sense, especially if the objectives have wildly different numerical scales.
Which brings us to the famous alternative, the Pareto optimization method. It's often called the gold standard because it maps out the entire trade-off space.
Right, Pareto optimization is comprehensive because it finds the entire set of optimal solutions. The Pareto front, where improving one objective means you have to sacrifice another. The failure mode here is scale and decision paralysis.
Decision paralysis.
If you have a complex problem, that Pareto front might contain thousands or even millions of solutions, all of which are technically optimal because none dominates the others.
And that's computationally intensive, I imagine.
Immensely. You need huge resources just to generate that front. But more importantly, it shifts the entire decision-making burden to the user. Imagine you're a doctor in a time-sensitive situation. You can't be presented with 500 equally valid medical treatment plans and be asked to choose.
No, the volume of solutions would just complicate things way too much.
It's the difference between having one prioritized choice or an overwhelming menu of choices.
Right.
And finally, you have evolutionary algorithms like NSGA2. These are powerful for exploring huge search spaces and finding diverse sets of solutions. They use processes inspired by natural selection, mutation, crossover, selection.
So they sort of evolve a solution.
They do, by iteratively improving a population of potential solutions. But they suffer from three major drawbacks. High computational demands, they're expensive to run, difficulty in interpretation, the logic behind the final solution is often hidden by this random evolutionary process.
And what's a third?
Their stochastic nature. It introduces variability and inconsistency. If you run the same evolutionary algorithm twice, you might get two slightly different sets of solutions.
Which makes it hard to guarantee consistent performance.
Exactly. So the lexicographic method, once you fix this tolerance flaw, it offers a consistency and interpretability that these powerful but, opaque alternatives just lack.
Okay, so now that we understand the strategic advantage of the lexicographic method, let's zoom in on the specific mechanism that makes this research work. The definition and application of tolerance. The research is very clear about distinguishing between absolute and relative tolerance.
It is.
If we just talk about tolerance, we're usually referencing an absolute value, right? A fixed number applied during optimization, like objective 1 must not exceed a loss of 0.5.
Correct. But the researchers intentionally avoided that fixed absolute value. Instead, the absolute tolerance value that's used in the algorithm is actually derived.
Derived from what?
It's calculated by multiplying the core relative tolerance parameter. That's the number the algorithm is actually trying to optimize by the current value of the primary objective.
And in this study, the primary objective was categorical cross-entropy, or CE.
Right. So if the current CE value is, say, 10, and the relative tolerance is 0.1, then the absolute tolerance allowed is 1. But if the CE value later drops to 5, the absolute tolerance allowed shrinks to 0.5. It's dynamic.
And this distinction isn't just academic, is it? It's fundamental to why this optimization works so well. Can you explain to the listener why using relative tolerance is the linchpin here? Why would absolute tolerance have failed?
This is really the punchline when it comes to balancing objectives. We are optimizing two things with wildly different numerical scales.
Okay.
We have categorical cross-entropy, CE, which is a loss function. It typically gives you small decimal values when the model is doing well, maybe
Right.
0.1, 0.5, 1.0. And then we have the L2 complexity, or the L2 norm.
Which measures the model's weights.
Exactly. And that can easily run into the hundreds or even thousands. I mean, 3,000 to 4,000 was common in this study.
Oh, okay. Big difference in scale.
Huge. And if we tried to use absolute tolerance, we would run into the exact same numerical bias problem that cripples the weighted sum approach. A fixed absolute tolerance of, say, 1.0. It means almost nothing to an L2 norm value of 4,000.
But it's catastrophic to a CE loss value of 0.5.
Exactly. The massive numerical disparity would cause biased or suboptimal solutions because the constraints wouldn't be equally meaningful for both objectives.
So relative tolerance acts as a true equalizer.
It does. By using relative tolerance, we normalize the impact. The tolerance parameter becomes a percentage of the current performance of the objective. This ensures the optimization process is balanced and meaningful, and it allows the algorithm to navigate these numerical disparities for a robust and fair optimization, no matter how big or small the objective's value is.
It's an essential precondition, then.
It is essential for any multi-objective work when you're dealing with different kinds of metrics.
Let's just solidify the objectives themselves. The study adopted this multi-objective approach for training a neural network using those two specific parameters, categorical cross-entropy and L2 complexity. Why that specific pair?
Well, CE, as you said, is the gold standard for measuring prediction accuracy in multi-class classification tasks. It quantifies the difference between the model's predicted probability distribution and the actual labels. So a lower CE means higher accuracy. That's objective one,
The primary goal.
the primary goal. And L2 complexity, or L2 norm, that's the regulator. It's a mathematical measure of the magnitude of the network's weights. When the L2 norm is high, it means the model is using these very large, complex coefficients.
Which often leads to overfitting.
Exactly. It performs perfectly on the training data, but then miserably on any new, unseen data.
Yeah.
The L2 norm penalizes these large weights. It forces the network to keep the model structure simple and the weights small, which helps with generalization.
So it's a classic MOO conflict.
It is. You can drive CE, your accuracy, down to near zero, but you often pay for it by letting L2 complexity spiral out of control. You get a brittle, overfit model.
And conversely, if you force the L2 norm down too much,
You get a highly generalizable model, but its ability to even fit the training data might suffer, and you end up with poor accuracy. So the study aims to find the optimal trade-off point between these two fundamental requirements for any successful ML model.
Okay, before we get into the dynamic algorithm itself, the foundational experimental setup is crucial. As you mentioned, the researchers were really meticulous about keeping the environment simple and consistent.
That consistency was vital. It was all about isolating the variable they were investigating, which was the multi-objective algorithm and the tolerance optimization. If they'd used a huge, complex transformer model, any result could have been blamed on the architecture rather than the method.
Right.
So they used a very simple, consistent neural network architecture across all their tests, a basic multi-layer perceptron. It had an input layer of 784 nodes.
For a flat 28 by 28 pixel image.
Correct. Followed by two dense layers, the first with 50 neurons and the final output layer with 10 neurons for the 10 classes they were classifying. They used real U activation for the hidden layer and softmax for the output, which is all pretty standard for multi-class classification.
And even the initialization was kept extremely basic, weights randomized in an error range, biases set to 0. This emphasis on simplicity, it really reinforces the eventual conclusion.
Which is that the power came from the optimization engine, not from the specific model architecture.
Right. And to test the generalizability of that engine, they used 4 very different benchmark datasets.
They did. They needed to prove that finding the optimal tolerance wasn't just some fluke specific to one type of data.
Yeah.
So they had the classic MNAShes for simple digit recognition, which is relatively straightforward,
And then fashion mist.
which is significantly tougher. The textures and features of clothing are much more complex and less distinct than clear digits.
And then they moved into medical imaging.
Crucially, yes, 2 medical imaging data sets from MedNist, pneumoniumnist, and breastmnist. And these are highly challenging because they involve intricate, often sparse medical data where even small errors can have severe consequences.
So the balance between accuracy and generalization is intensely relevant there.
Exactly. The 4 data sets provide a really robust spectrum of difficulty for recognition and classification.
Okay, let's get to the mechanism itself. The multi-objective algorithm designed for this dynamic tolerance adjustment. This is where the machine learning really happens. It's an iterative process that systematically sweeps a range of relative tolerance values to find that Goldilocks zone.
The single optimal setting for that specific data set.
Right.
Let's break down the training process in detail following the exact steps they used for each data set.
Okay.
Step 1. Establishing the hierarchy. First, the priority is fixed. CE for accuracy is the primary objective, and L2 norm for complexity is the secondary. That order is non-negotiable.
Lexicographic method.
Exactly. Steps 2 and 3 are initialization. You find a loss function, set up the neural network structure, and crucially, before you start, you establish a specific predetermined range of relative tolerance values to investigate, a window of potential optimal values for that specific data set.
And then step 4 is the big one.
Step 4 is the sweeping run. This is the core operation. A complete, isolated training run of the neural network is performed for each single relative tolerance value within that range. So they tested 33 solutions. They ran 33 full training cycles from scratch.
And now for step 5, this is the critical internal loop where the lexicographic power meets the tolerance parameter. How does the model actually train and manage that compromise dynamically?
It starts with the primary objective, CE. So substep A. The training starts focused solely on minimizing the CE loss function. The network is just trying to get as accurate as possible.
Okay.
Substep B. Training proceeds epoch by epoch until the optimization of that primary objective is, well, effectively achieved on the validation dataset. You're trying to max out the CE performance.
And only once that performance plateaus.
Only then. Substep C, the transition. The algorithm proceeds to the next objective, the L2 norm. And here's where that relative tolerance is activated as a constraint manager. The algorithm now wants to minimize the L2 norm, which means minimizing the size of the network's weights.
And to do that, it might have to slightly increase the CE loss it just achieved.
That's substep D, the trade-off calculation. This is the crucial part. The relative tolerance value dictates the absolute maximum increase in CE loss that the system is allowed to accept in exchange for reducing L2.
Okay, so let's walk through an example. Say we reached a primary CE loss of 0.10, and our relative tolerance for this specific run is set at 5%.
That means you have a margin. The algorithm is now trying to drive the L2 norm down. If optimizing L2 requires the CE loss to creep up from 0.10 to, say, 0.103.
That's an increase of 0.003.
Right. And since our absolute tolerance limit is 5% of 0.10, which is 0.005, that move is permitted. The algorithm successfully compromises the primary objective a little to get a huge advantage on the secondary one.
But if reducing L2 required CE to jump to 0.106,
That move would be rejected. It violates the 5% tolerance constraint.
so it's constantly performing that delicate balancing act. That makes the role of the tolerance value crystal clear. It's the precise, quantifiable margin of acceptable sacrifice.
Precisely. If the relative tolerance is tight, say 0.1%, that compromise window shrinks dramatically. The system prioritizes maintaining CE performance almost entirely. But if the tolerance is loose, say 25%, the algorithm has massive flexibility to compromise CE to aggressively minimize the L2 norm.
And it just keeps going in that loop.
It does, substeps E and F. The algorithm continues in this iterative compromise loop, minimizing L2 under the CE tolerance constraint until it can't optimize L2 any further without violating the set tolerance. And that completes the training for that one specific tolerance value.
And then, of course, the researchers collected all the data, accuracy, CEL2, training epochs, and total training time, which leads us to the final analysis step. How did they determine the best solution? Because this analysis had to synthesize two wildly different numerical metrics, CE and L2, into a single comprehensive measure of goodness.
Right, so first they had to manage the data structure. They transformed all the evaluation metrics into tensors. For listeners who aren't constantly in ML frameworks, a tensor is just the fundamental data structure. It's basically a multidimensional array, highly optimized for speed on GPUs.
So that made the comparison process fast and efficient.
Extremely. Secondly, they were rigorous about normalization. Since L2 and CE are on completely different scales, 0.1 versus 4,000, just averaging them would be meaningless. The L2 term would totally dominate the mean.
So normalization scaled both metrics to a comparable range, like between 0 and 1.
Exactly, to ensure a fair fight. And once they were normalized, they just calculated the mean of the normalized values to create a single aggregate performance measure. The network configurations, the models trained at specific tolerance values with the smallest mean normalized values, were identified as the top performers, the best solutions.
So this wasn't just plotting a standard Pareto front. They were analyzing the internal effectiveness of the tolerance parameter within an already high-performing lexicographic framework.
And that provided this deep analytical insight into the methodology itself.
So the results. What was the first big takeaway?
The results immediately validated the entire effort. The primary, most striking conclusion was that the optimal tolerance threshold varied wildly and significantly across every single data set.
Even though they were using the exact same simple neural network and objective.
Exactly.
Yeah.
And that finding right there, it just emphatically destroys the viability of any one-size-fits-all or ad hoc tolerance selection. The landscape is entirely problem-specific.
Let's break down those optimal values because they are jarringly different. We're talking about optimal tolerance ranges that vary by an order of magnitude.
They do.
Let's start with the MNE digit recognition dataset. This is the easiest one, known for high contrast, distinct features.
And for MNIST, the optimal tolerance was pinned down in a very narrow window, between 20.25 and 24. The absolute optimal value was determined at 23.5313.
And that produced a top model accuracy of 0.9732.
Right, with a CE of 0.0949. Now contrast that massive tolerance value, 23.53, with the Fashion MNIST dataset.
Visually similar, 28 by 28 images, but the features, the textures, and folds in clothing are much harder to distinguish.
Much harder. So the complexity requires a much tighter grip on the model's own complexity. And the optimal range shifted dramatically, went down to between 4.75 and 5.20. The final optimal tolerance was nearly 5 times smaller, at 4.9983.
Wow, why a huge difference?
Well, fashion MNIST requires the L2 norm to be really tightly controlled to prevent the model from overfitting to superficial details, like individual pixels of cloth texture. A large tolerance, like 23.53, would have compromised CE way too much in favor of a recklessly low L2. So the complexity of the data itself dictated a much lower, tighter optimal tolerance setting to maintain accuracy.
So the algorithm learned the inherent difficulty of the data.
That's a great way to put it. We see similar necessary tightness in the medical data. For pneumoniumnist, the relevant range was between 14 and 18, which led to an optimal tolerance of 14.1250.
Okay, so another distinct value requiring customization.
Yes, and these three data sets, MNIST, fashionist, and pneumoniumnist, they all shared a common optimization landscape pattern, which the researchers dubbed Pattern 1, irregular fluctuations.
Meaning what exactly?
Meaning that in Pattern 1, as the tolerance value varied within that optimal search range, the resulting metrics CE, L2, and accuracy, they didn't change smoothly. They had these abrupt, irregular spikes and dips. The landscape was volatile.
And the genius of the algorithm was its ability to navigate that turbulence.
And pinpoint the singular needle in a haystack sweet spot that provided the best overall balance of both objectives.
But the last data set, breast mistist, showed something completely unique. This was pattern 2, regular or systematic behavior.
It was. Here, the optimal tolerance was found in a tiny range, 0 to 5, resulting in a minimum value of 0.7813.
Much, much smaller.
And what stands out here is the regularity of the relationship between the metrics and the tolerance input. The categorical cross-entropy, CE, it showed a clear, distinct exponential relationship with relative tolerance.
So as tolerance went up, CE went up exponentially.
Right, signaling that any flexibility was instantly punished by a rapid drop in accuracy. Conversely, the L2 norm showed an inverse proportionality to relative tolerance. It decreased in a predictable, systematic way as tolerance increased.
So that regularity, it made finding the sweet spot a whole lot easier.
It did, though it was still highly dataset specific. It suggests a cleaner, less noisy trade-off frontier for that particular medical classification task.
That contrast, the volatility of pattern 1 versus the systematic exponential rise of pattern 2, it truly highlights the need for this automated approach. I mean, a human guessing a tolerance value would never know if they were stepping into a volatile landscape or a systematic one.
Not a chance.
Beyond the optimal values, the researchers identified 2 extremely important consistent phenomena that held true across all 4 datasets.
And these provide fundamental insights into the lexicographic method itself.
Yeah.
The first phenomenon is the plateau effect.
Which defines the boundaries of the optimization problem.
Exactly. For every single dataset, the moment the tolerance threshold moved far outside that optimal range, the metrics just stopped changing meaningfully. They reached a plateau or stabilized. And this behavior is the algorithm's way of screaming that the multi-objective challenge has been artificially reduced back into a single objective problem.
Okay, so let's elaborate on the consequences of the 2 extremes, because they really illustrate the failure modes of manual selection. What happens if you manually set a low tolerance? Say, way below 20.25 for that MNIST example.
If the tolerance is too low, the constraint on objective 1, the CE, and accuracy becomes so strict that the lexicographic engine focuses almost exclusively on it. It maximizes accuracy, but at a huge cost.
Which is
The consequence is that the algorithm barely allows any compromise, even if that compromise would stabilize the model. The L2 norm, the model complexity, is unduly penalized and allowed to explode. For MNIST at that low extreme, accuracy might stabilize at 0.96, but the L2 norm skyrockets to an unhealthy 3,400.
So you get a model that's highly accurate but brittle and overfit.
The optimization effectively became maximize CE at all costs.
And what about the other extreme? High tolerance. If you set it far too high, say 30 for MNIST, well above that 24 threshold.
Then the constraint on CE is so loose that the algorithm shifts its focus entirely to optimizing the L2 norm, the secondary objective, and it achieves this goal. For MNIST, L2 might drop drastically down to 4.0 times 10 to the minus 4.
But at what expense?
At the catastrophic expense of accuracy. If the tolerance is too loose, the system readily sacrifices CE for L2 gains, causing accuracy to plummet to useless levels, like 0.09.
So the optimization became minimize L2 at all costs.
The plateau effect is crucial. It confirms the optimal tolerance range is where the metrics are volatile, where the trade-off is actively happening, and it defines the boundary, where the multi-objective problem collapses into a single objective one.
That detailed explanation makes it much stickier for the listener. The second consistent phenomenon relates to computational efficiency, training time escalation.
This was a clear and consistent trend across all the datasets. As the researchers moved from lower to higher tolerance values, the total training time showed an irregular but undeniable escalation.
Why does that happen?
It's directly linked to the flexibility that tolerance grants the algorithm when it's optimizing that secondary objective L2. Higher tolerance increases the maximum number of training epochs required to optimize the L2 norm.
Ah, because the algorithm has more wiggle room to compromise CE, so it takes more steps to exhaust all the L2 minimization possibilities under that looser constraint.
That's it exactly. A high tolerance essentially gives the algorithm a license to explore additional iterations for L2 optimization before it hits that tolerance ceiling. And this broader exploration space, while it might lead to a better L2 value, it directly elongates the training duration.
So the optimal tolerance isn't just the point of best metric balance, it's also the balance point between performance and computational cost.
Finding the optimal tolerance minimizes unnecessary training epochs.
That's a huge practical takeaway. A poorly chosen, overly large tolerance doesn't just potentially wreck your accuracy, it slows down your entire development cycle.
That's right.
So while the research delivered these powerful, transferable insights, it is important to acknowledge the real-world constraints the team was facing, especially with computational resources.
It is. The study was constrained by limited available RAM memory, and this dictated the scale of the investigation. It limited the depth of the Pareto curve exploration they could do,
They were limited to generating up to 33 solutions per dataset.
which means they couldn't sweep through a truly continuous spectrum of tolerance values. However, I think we have to view this limitation through a lens of success.
How so?
The fact that they achieved highly competitive and excellent results with such a small, constrained sample size, only 33 points generated, that actually underscores the immense power and efficiency of this automated tolerance optimization approach.
So it suggests that even coarse-grained sampling, guided by this systematic method, can zero in on optimal performance remarkably quickly.
They maximize their resource utilization exceptionally well, despite the limitations.
We also need to reiterate the deliberate choice of that simple neural network architecture. I feel like I have to ask. If the ultimate goal is real-world application, say running this MO framework on a massive modern LLM or a complex medical imaging transformer, doesn't using a basic simple ANN architecture artificially inflate the importance of the tolerance finding? How can we be sure this result holds true for models with billions of parameters?
That is a critical point of inquiry. And the researchers would argue, and they deliberately structured the experiment this way, that they needed to prove the concept of the lexicographic engine itself. By achieving satisfactory results with the simplest possible structure, they proved the algorithm's capability to deliver exceptional outcomes and established its fundamental robustness.
So the implication is not that the simple ANN is the solution.
No, but that the optimization technique is model agnostic. The power lies entirely in the automated lexicographic engine, not the specific vehicle it's currently driving. This approach is highly portable. It can be applied to any machine learning model, whether it's a simple multi-layer perceptron or a gargantuan language model.
And that framework portability is key to industrial adoption.
Absolutely.
Looking ahead, the current study focused on balancing two objectives, accuracy, CE, and complexity, L2. But real-world MO problems often involve many more, maybe 4, 5, or 6 objectives of vastly different natures.
Exactly. Future research is required to fully stress test this algorithm's potential when it's simultaneously optimizing a broader, more heterogeneous set of objectives. The current study proved the foundational mechanism, but rigorous validation across larger objective sets is still needed.
Did the researchers suggest any pathways for that validation?
They did, and they're extremely exciting. They focused on optimization metrics that are rapidly becoming mandatory for real-world model deployment.
Such as?
Imagine optimizing not just for accuracy and complexity, but simultaneously for fairness, to ensure demographic parity in predictions,
Okay, that's a big one.
and interpretability, to build confidence in the model's decision-making process, and energy efficiency, to minimize the computational power needed, which has massive environmental and financial implications.
Those three are incredibly difficult to quantify, and they're constantly in conflict with basic performance metrics. I mean, fairness might reduce overall accuracy, for instance.
Precisely. Fairness metrics are usually discrete and statistical. Interpretability often involves complex regularization terms, and energy efficiency is measured in hardware performance metrics. They're all wildly different from CE and L2.
So if you can get this to work,
Successfully integrating, prioritizing, and balancing these diverse, complex objectives under the automated lexicographic framework, that would fully solidify the algorithm's broad applicability and establish it as the definitive tool for complex, real-world MO deployments.
so let's bring it all together. What is the profound impact of this research?
I think it's that it has successfully delivered a systematic, reliable, and reproducible pathway for automatically determining the tolerance level in lexicographic multi-objective optimization. It completely eliminates the subjective guesswork and the inconsistency that really plagued this method previously.
So this automation provides a clear, consistent benefit.
A demonstrable improvement in model performance, better generalization, and enhanced computational efficiency. The study definitively proves that the optimal tolerance is highly dataset specific, which reinforces the absolute necessity for this custom, automated, data-driven approach. You just can't pull a number out of thin air anymore.
Ultimately, this work results in the creation of a potent, adaptable tool for multi-objective optimization. It empowers even the simplest neural network structures to significantly amplify their effectiveness and achieve commendable, robust results in complex tasks simply by automating one critical, previously overlooked parameter. It removed the human error from that foundational process of defining what an acceptable compromise is.
Well said.
So we'll leave you with this provocative thought. If simply automating a single foundational parameter, the tolerance that dictates acceptable compromise, can unlock this much efficiency, consistency, and robustness across wildly diverse datasets, what other foundational, deeply ingrained ad hoc assumptions are we making in modern ML optimization? What other areas are ripe for disruption by applying machine learning to the optimization process itself? The concept of meta-optimization using ML to perfect the very way we train and tune ML models is not just a promising idea. This research suggests it is the next great inevitable frontier.